Yes. Good evening, good night, good morning, everyone. Thanks for coming. I'm Moritz Heidkamp, and this is my presentation about, well, transcending places, as you can see. And when we transcend places, we could instead program with values. And what that means is, oh, the resolution is a bit too small, I guess. What this means, to understand what this means, we first have to understand what I actually mean, or we actually mean by places. So before we can transcend something, we have to understand what it actually is. This is what the first part of the presentation will be about. The next part will focus on what the problems are with this approach, and thus why we may want to transcend place-oriented programming. And then I would suggest or present an alternative or a different approach to implement or to build systems that is focused on or focusing on values, which is inspired by a programming language called Clojure, which is invented by a person called Richicki. We will hear him or see him in that part. And then I will try to explain how you can model state with values, but this will be clearer later, and give some practical examples of already value-based systems you all might know, but you weren't aware of that they are, maybe, because this terminology is not very common, so we don't refer to places usually when we program, but we will see what that means. I uploaded the slides to the FRAP system, but I think the Fahrplan generation is a bit manual, so they weren't linked, at least earlier today. So this is the URL for those watching the live stream if you want to follow the presentation on your own machine. Okay, so let's start out with what actually is a place in that context, or in the context of our model here. Well, the easy way to think about it is, or an easy mental model is that a place is some box with some content, right? So, for example, the contents in that box can change. And another property of a place is that you can only convey it by reference. So you can only pass around something that is a place by means of its reference. So what does it mean? It's a bit abstract. So a common example, or a very well-known example, is objects in classic object-oriented programming. This is some JavaScript where you have an object that has a field, and I can reference with multiple names to the same object. So P is a reference to the object O, but if I change object O state, then I also change object P state. So there's a place that can be referred to, but all the references refer to the same place, and this place can change. Very simple. Everybody knows that, I suppose. So what else are places? Basically, the fundamental building blocks of our of machines that we use are places. So memory is a place. So I can address memory by means of a pointer and mutate the contents of the memory. Or files and file systems are just places where I can put stuff, can read stuff, I can put stuff, but it can change at any time. I have no control over change. And same for most database systems. So relational database systems, for example, key value stores, whatever. They're just places where I go and can look into the contents, but I can also put stuff, but there's no way to coordinate that by default, basically. So I already hinted at what problems are there with places. So something that maybe not everyone has run into, but when they run into concurrent, or when you write programs with concurrency in them, which is not very rare these days, you probably have run into a problem like this. So you have a variable that is, as we learned, a place with some contents. Then you have one thread that starts stating its intent that it's going to sum the contents of x's, which is 1, 2, 3. Then initialize another place. This is where we keep the result, and then we just iterate this array and sum it up. But at the same time, concurrently, there's another thread of control that can refer to the same place. And it might update the place or change the place without this thread knowing. So if we are unlucky, this operation is executed perhaps while we are inside this loop, of course. So this is a classic race condition. And this will lead, if the timing is bad, will lead to the wrong result. So the program will say, okay, I'm summing 1, 2, and 3, and then it prints 8. So we will assume the program is wrong or something. Well, it is wrong. It doesn't take into account that this place might change at any point in time. So this is a problem, right? Well, you might say, I'm not that fancy. I usually don't write multi-threaded programs. I only have a straight one-thread programs like, I don't know, I'm a Node.js programmer. But still, you have the same problem, basically, unfortunately, because, as I said, you can only pass a place by reference, by referring to it. So I could have the same program, but after printing my intent to sum this list, I call some other function, innocently looking function that does some pre-processing, whatever. But what I pass here is again a reference. So I have basically no idea what this function is going to do to my access. So whatever this prints, it's out of my control if I don't know what the function preprocess does, because it has unprotected control to this place I pass to it, right? So no multi-threading involved here, but you still have the same problems with because of remote effects. And also in event-driven programming, you have this the callbacks may run in a different order than you expect, and then you have the same effect, right? So to work around this, there are means of coordination required, right? So everyone probably knows a trick called defensive copying. So in JavaScript, this is a bit weird because there is no copy operator, which already tells a lot. So to copy an array, I call the function slice, which should give me a slice of an array, pass no arguments, and then it gives me a slice of the whole array. So I have a copy. And now if somebody else changes access, the third slot of access, access will be changed, but my copy will not be changed. So that's a way to work around this. I first copy the thing, and then I'm going to do some non-atomic operations, which prevents this problem. There's even some kind of pattern that you have to do this. You actually should do this with all kinds of getters, which return places whose return value is a place. For example, if we have a function throp here that we just want to pass the options of Snortle to, it's a bad idea to do it like this, because this gives the function throp unprotected access to my internal field here. Options might be a private field, and it's nobody's business. That's why I have a getter, right? But the getter doesn't help in this case because the options object is still just a place, and it can be mutated in whatever by some other component, which I don't even think about when writing this code. So this is dangerous. And the common pattern to do this, or to work around this, is then to make the defensive copy in the getter. Whenever I return my place or complex object, I instantiate actually a new object. And this has all kinds of other problems, of course. This assumes that this is a mutable object, of course. You could have immutable objects which don't allow changing in place, but this is only, it's not so nice in most of these programming models. It's also pretty wasteful because I have to copy this object every time somebody calls my getter, even though the other party might not be interested in changing this, or maybe just wanted to look at it. So I produce a lot of waste. Another option is to use logs. So I would wrap my critical section in some kind of synchronized block. This is just made up. I don't know if it actually exists in JavaScript. So before I print and sum my access, I just say this section is synchronized. Well, this works, but it has some significant drawbacks. So first of all, I block all the readers and the writers. So I only want to block writers, but I also block the readers while I'm doing this, because while my critical section is running and I'm changing the place maybe, it might have an inconsistent state, so readers should not see that. That's why I also have to block readers. And of course, the more readers and writers there are concurrently, the slower this gets, because the contention rises and everyone has to wait in queue to do something to the place. I can accidentally lock two large sections of code. So I don't actually need this. I don't know. I have a critical section in the middle of that. I do download a file from the internet or something like that. And while I'm doing that, the place is locked, and it's just the level of coordination is too coarse. It's not optimal. And of course, everyone who has dealt with that probably also ran into deadlocks, which are annoying to analyze and annoying to fix, sometimes impossible. And of course, everyone has to participate in that protocol, right? So the synchronized here is something that the user code has to do. If I could hard code it or code it into all methods, for example, my object exposes that they are synchronized, but then I have a problem that I can't call them unsynchronized anymore. So, or have a spanning transaction of changes in the same synchronization block. So all users have to think about this, and it leaks into your code, which is also not very nice. Another problem with this model is that it actually destroys information. What does it mean? So if I change a place, like in this case a database record, what I do is I replace the last name in this case, and I forget who Kim.com, that Kim.com previously was Kim Schmitz, right? There's no trace of this information left in the system. It basically destroys my information I had. Because in the reality, it's perfectly clear, we know that at some point in time he referred to himself as Kim Schmitz, and then there was a point in time when he started referring to himself as Kim.com. So this information is not lost, but in these kinds of systems, it gets lost by default. So, as I said, Rich Hickey, who is the inventor, among other things, of Clojure, refers to this style of programming to place-oriented programming, or he made up the acronym PLOP to make it sound a bit silly, maybe, I don't know. But it's a very apt description, I think, because place-oriented means this is your default, and this is the traditional default, yeah, right? So when I start out building a system, I usually work with places. When I start building a system with object-oriented languages, I pretty much have to use places all the time by default. And he argues that this default is born out of space and performance constraints of the time when these concepts were invented, because in the 60s and 70s, we didn't have much memory, for example, and also not much computing power. So we had to find ways to reduce or to reuse the little memory we had. But today, this is not the case anymore. So he argues that with gigabytes or even terabytes of RAM in one machine, there's just no point in prematurely reusing places, because we just have so much space, right? Same. It's a bit like when garbage collection was new or introduced into mainstream languages, everyone was, or many people were opposed to that and say it's very wasteful and garbage collection is inefficient. I'd rather do it by hand. So memory management code leaks through the whole code base, and by now I think the paradigm has shifted, that we by default use garbage collector languages and only drop to manual memory management when we have to, for performance reasons or whatever. So what he proposes is a value-based approach, as I in my title hinted at in my title, a value-based approach. And to understand what that means or how that works, we first have to understand what a value actually is. So we casually refer to things as values, but there's no clear idea in your head, I guess, what a value means, right? Maybe for some of you. So one very important, or the most important property of a value is that it is immutable. It cannot change, right? And we know this from numbers. Numbers are basically the only thing that are really values in, I think, in all IT systems, in all programming languages, and in all databases, whatever. So I cannot change the global notion of 23 to become 42 and everywhere. It's not possible. And if it would be possible, it would be insane, right? Everyone agrees with that. If I had an operator, I don't know, if my plus operator would be able to change the value I pass to it to a different thing, that would be insane because you cannot reason about this anymore. But still, we do this by default with all our other values, right? So immutability is paramount for this approach. So whenever we refer to a value, we mean something immutable, and this is easy to imagine for atomic things like numbers. I already mentioned that, symbols or characters, whatever. Those are easy to keep immutable. But this also has to be extended to compound or composite to composite structures like strings or vectors, sets or maps, whatever you use. To make it possible to refer to them as a value, you have to make them immutable. So this sounds a bit tricky, but it can be done efficiently by means of something like implementation tricks like so-called persistent data structures, which are based on a concept called structural sharing, that when I have a vector of, I don't know, 10 elements, and then I want to add another one, I don't allocate 11 elements, copy all of them over and add a new one, but I just refer to the existing vector because I know it will not change anymore. It's immutable, it's a value. And then I will just have another place where I put, this is implemented in terms of places, of course, because the lowest level is a place, or is place-oriented. So then I have another place that just contains the new element I want to add and refers to the existing vector for the rest, right? So I can implement some structural sharing. There are many advanced implementation strategies to make this very efficient. So this is not naive copying. It's still efficient, but it allows me to refer to composite structures as values, which is a trade-off worth doing here, as we will see. Another property of values, which emerges from immutability, basically, is that values are independent of their location. So it doesn't matter if I put a number on your machine or on my machine, it's still the same value, right? And if I extend this notion to composite structures, it gets even more powerful. So suddenly I can easily cache values, for example, because I know they won't change. When I have a value and it's on my machine or on some intermediate machine in a pipeline, I don't know, it's no problem to cache that because I have a guarantee that this will not change if I have a value-based system, right? This is very powerful. I can also easily distribute this. I can have a large composite value, and then I can hand this off to 10 machines, and then they each of them work on a different chunk of the value, for example. No problem, because there's no central place where it can change. So values are shareable, right? There's no coordination required. When somebody refers to a value, I don't have to make sure that it's in a consistent state or anything while it's being referred to, while it's being copied or whatever, because it cannot change. Those are all emergent properties from they emerge from the immutability property. So here's an example that works right. So I use numbers in this example because that's easiest to understand for if you don't have pervasive values. So, and this is very natural to us. There's no surprise here, right? So I have x and y, and then I have y, like in the original example at the beginning. So where I had an object. Now y is x. If I change x here with x++, and then I also pass y to Frobnicate, which calls ++ on its argument, I still have I only see the effect on x here because I changed the contents of the x reference. But the y reference has not changed a bit. And this is no surprise to all of us, I hope. And this is what makes programming with values very worthwhile, because there's no way that the Frobnicate function can change my y. There are guarantees that just prevent that. Of course, in case of numbers, it's cheap to just copy them. So that's why all systems have that. But extend that to composite structures and you get a lot of leverage. So you might argue, but things in my system change, right? If I want to build a real application, I have to have some kind of state. For example, I don't know, I have a server and then there are sessions of connected clients, whatever. this is something that changes and requires, requires me to keep some state in my process. So how can I build this when my values are immutable? This is not possible, you might think, at first sight. So we have to think of something, how to model state with values to get around this problem, or to make this possible, right? And one way to do that is by means of the epochal time model, as it is implemented in Clojure, but there are other implementations of the same idea. And I think this is not like a canonical name for that. It's just how it is referred to in the Clojure universe, so bear with me. And to understand how to model state with values, we first have to understand again what actually is state, right? So just like we did with values now, we have to understand or get an idea of what we define state to be. And so the definition Richicki came up with is this. State is the value of an identity at a point in time. So that sounds pretty abstract. Gotta take a sip. Now we have two new concepts here suddenly. And we need these concepts in order to model state by means of values. So first of all, let's take a look at this picture. It's this is a series of photographies taken in 1887 by a guy called Edward Muybridge. He took that before the invention of the film camera as we have today, by means of placing individual cameras in a row, and while the horse was riding by, one of the other was triggered. So then you get a nice series of pictures of the movement of this horse and the rider on top. And you could say, or what we refer to in the epochal time model as state is one of these instances. So the green outlined horse rider here and horse combination is the state of the identity, which we'll look at in a second, at that point in time, right? One state at a certain point in time. So what is an identity? Identity is a succession of causally related states over time. Okay? Easy. So what we just saw, the horse, basically we can think of the horse and the rider as the same thing, even though it changes over time. So in the first panel, it looks like this, and in the next panel, all legs are in the air, whatever, but we still perceive the whole thing as one identity. That's what we mean by identity. So identity is not a name or anything, it's just the concept of an entity that can take on new values over time, but you perceive it as a whole. So what is time? Time is just a relative notion that orders states. So it's not like a coordinated absolute time like we use it. I don't know if that's even physically correct, but it's just about something is before, something happens now, or something is the case now, and something is the case after that. So it just imposes some order. There's no independently running time or whatever. So in this case, each picture is one point in time. So whenever we take a picture, we create a new point in time, right? So it's not a continuous thing. It's just whenever I need a new value for a certain identity to produce a state, I just say this is the next point in time, and it's relatively positioned to the one before that or the one after that. So what we need to produce time or to work with state is that we need to have some kind of change. And change then means that we transition the state of an identity from one point in time to the next, right? As I just already summed up, I guess. Because a state and point in time, as I said, is just a value, basically that means that change is a pure function. So I put in the value of point in time x, and I get out the value of point in time y. So I can repeat this process, for example. All kinds of advantages that I get from working with pure functions are suddenly available to my stateful system, right? Because I can just apply the function again to simulate something else or whatever. So change is a succession of function applications. What is a function, for those of you who are not familiar with the concept of a pure function? All you have to think about is that a function is just a mapping of an input to an output value, and whenever I put in the same input value, I should get out the same output value, no matter how often I call it or whatever. I could even replace the application of my function to an input value with its output value, because if we apply the notion of value as I described it, I know they will not change. This property of functions is called that they are referentially transparent. You will run into this. And you could also say they are idempotent. So there are at least no essential side effects. Of course, my pure function could still do, I don't know, logging or debug logging, for example, right? This is something that changes the behavior of the function, but it doesn't change the essential operation of the function. But that's just an aside. So in this model, change does not happen in place, as I've seen, because when I transition from one state to the next, I do not change the state before that, but I produce a new point in time that just refers to a different value. And this means I do not change in place, right? So somebody referring still to the old or to the previous current state will not suddenly get the new value I produced by my change function. And to do this, at least in Clojure, you have to have some kind of managed reference. This is just a word I use here. It's not a canonical terminology again, just to differentiate it from the references we had before. So what is a managed reference? It's something that allows me to represent identity and thus to represent change in a value-based system. Yeah. So I would have with the horse example, I would have a reference to the combination of horse and rider. So this is my identity. It has a certain value, and it has to support two operations to make this work for stateful systems. And one of them is obviously change. Again, not change in place, but apply a pure function to one state to produce a new state, and then update the reference, only the reference that our managed reference it represents, to contain or to refer to this new state. And there are several different ways to implement these references. Two of them I listed here: compare and swap. So I produce a new value, see if it's still the case that if the current value is still the same I expected. If not, I apply my function again to the new value until I succeed in updating the reference. Or another thing is software transactional memory, which allows me to coordinate these updates across multiple identities. These are just two examples. There are more. You can think of more. Another option or another operation we need is to perceive a value, or to perceive the current value or some value of a reference. So this is the other operation we need on a managed reference, and this just dereferences some point in time and gives us a reference to a value, or a value. Yeah, let's say it gives us a value. And again, this will not change. So that's what is perception. It's just obtaining a snapshot basically of one of these horses, right? So I look at the horse at some point in time, and I just get an impression of that in my mind, and I can keep that value or that snapshot in my head as long as I want. So it's very easy to do that with values because I know they won't change. I just hand out the reference to the value, and the perceiver can keep it around as long as they want. And that doesn't require any coordination, right? Because whenever I decide to perceive the value of a reference, the reference can tell me what it's currently referring to. And because it's managed and it does atomic updates to itself, there's no chance that I get an inconsistent view on the current state of the reference. So it's easy to just hand out the current value. It's just the one memory access, basically. So again, I can freely decide when to perceive the state of picture 11 when the horse actually rides by, and I look at it. I get this picture with a certain time delay, and of course, and stuff like that. That's always the case because there's distance. But I get this impression. I can close my eyes and keep it in my memory as long as I want, and the horse will just continue to ride. So there's no need to stop the scene to perceive what's going on. Right? That makes immediate sense in the real world. And we have to. Well, the idea of value-based programming is to extend this to our information systems, so that we don't stop the world just to look at it, because that will slow down the whole world as the more people look at things, right? And that makes no sense. So, of course, there are some downsides to this approach, because one of them is that it requires more space. Of course, because there may be infinite amount of perceivers who refer to old states of a reference, and this can amass lots of memory, of course. Well, that may be considered a downside, but as I said in the beginning, memory is not really our constraint anymore. And if it is, then we can make compromises. But as long as we don't have to, let's do it. Why not? The same applies basically to garbage collection. Just because I have a garbage collected language or a system doesn't mean that I cannot leak memory, right? Because as long as I refer to an object, it cannot be collected. So the same applies here. I wouldn't really consider it a downside. It could put more pressure on the garbage collection or whatever, but maybe in a few years we don't even need garbage collection anymore, because we have so much memory, we can just produce all values and leave them there, whatever. Because the runtime of the program allows it to fill up the memory, or never allows it to fill up the memory. Might be an option. Another downside could be that there's a certain performance penalty when I create large structures. As I said, when I do these not in-place updates, but append updates of a structure, this can cause a lot of, it could cause performance issues. But for example, in Clojure, there is a notion of a transient that allows me to put a value into a transient state that has certain limitations of what I can do with it. For example, I cannot pass it on to a different thread. And then I'm allowed to actually change this transient copy of a value in place until I decide that it's now done. So I can do lots of updates in the same way that I would do to a regular place. And when I'm done, I turn it back into a persistent value or into a real value. And then I can hand it off again as much as I like. So there are ways to optimize certain situations where it might be impractical to work with values all the time. But again, first measure and don't optimize before actually having numbers on what your problem is. And definitely don't optimize by default, these kinds of things. So another downside is, of course, that you actually have to have a system that provides me these things. So I need to have, if I start out with, say, Java or Ruby, the data structures just are not values, right? So they are fundamentally place-oriented, and I would have to re-implement my whole standard library, basically, to work with values before I can start doing anything useful. So that's not really practical, I guess. Of course, there are languages that provide this out of the box. I mentioned Clojure. The Haskell is also a candidate. All functional programming languages basically work that way. Some have different focuses, of course. But it's also possible to implement these data structures on top of, say, Ruby. And I think, yeah, especially for Ruby, there is an implementation of some of the persistent data structures I mentioned. And of course, it must be possible, because fundamentally all machines are place-oriented. So if I can implement this kind of thing in Haskell, I can also implement it in Ruby. Or for Haskell, if I can implement Haskell on top of a real-world machine, that's what I mean, I can also implement these kinds of things in an existing place-oriented programming language on top. But there are also, of course, the upsides, and these outweigh the downsides, in my opinion. One of them is that I don't require any, or at least less, explicit coordination. Sorry, I need to take another sip. So some reference types require some kind of coordination. That leaks into my code as well, as when I do software transactions, for example. That's another topic, but the default is, if you work with values, there is no coordination, and that's nice. You don't have potential for deadlocks or anything. It's just gone, because there is no need to lock things when I want to look at them or change them. It's also easy to test, but that's more an extension or a property of functional programming, I think, because you can just look at one specific function. Well, the nice thing about this change model is that because my update operations basically are pure functions, I can test them in isolation, and I can make up some state which represents the whole system state, and then I can put it into my function and see if the expected state falls out. So I don't have to stop the system and look at all the current states of all objects in my system or anything, which might be even impossible if it's a multi-threaded application, right? So that's really nice. And of course, no information is ever lost because we don't do in-place updates. So as long as somebody is still referring, there's a managed reference that's still referring to a value, or as long as there is some perceiver who dereferences the value and keeps a reference, or holds it, this information is not lost or destroyed while I'm holding it in my hands, right? So to give an example again, or the same example as in the beginning, how it would look like in, for example, Clojure, which using these concepts. The code structure is very similar, it's just a bit more parenthetic. And here is where we use our this managed reference thing called an atom. An atom is a compare and swap reference. So I put the list again into this atom and name it X's. Now thread A, the first thing thread A does is that it dereferences X's, which returns to me, so I give it a name or an alias, whatever you want to call it. C axis for current axis, and this is the reference to a value now, and this cannot change, it's a value. And no matter what thread B does to axis in the meantime, so here it swaps in the value 5 at index 2, like in the JavaScript example, in the original JavaScript example, no matter what is going on with axis while I'm holding onto this value, it's never seen inside my actual usage of that value, right? So current axis cannot be changed while, it cannot be changed during my threads running here. And this will always print 6, so makes sense, right? And you see it's not very complicated. It's not more difficult to write a program that way, but it's more robust. So, as promised, I will give some practical examples of value-based systems you already know, probably. But you may not have thought about them in that way. One thing is representational state transfer, at least when done right, I guess. I think the original intent of REST is indeed to have something like a value-based system across the web. So to see what makes this a value-based system, we have to identify the three components of what are the identities in a RESTful system, what are the values of a RESTful system, and what are the change functions of such a system. So identities in REST are usually called resources, and in its implementation in the web, it's usually you use URLs to refer to such a resource. So this is the identity that can change over time, right, in a controlled way. And values are the that what you can see of a resource is its representation. So when you get some, when you get a value, resource, you get a representation of it, and that is a value because it gives you a copy basically. And change is modeled by means of exchange of these resource representations. But of course, this can go wrong again. If I do something like this, I get the current state of the resource, and then I put back a new version of that. I have the same again as in the same problem again as with place-oriented programming, because whoever may have put something else, a different resource at that place before, that information is lost. So there's no inherent value-preserving property in REST, only if I do it right. So what I have to do is incorporate time again. So the main takeaway is that to make time in our changing system a first-class property. So what we do is use the E-tag mechanism that is also present in HTTP, for example. Sorry, I use HTTP as an example of REST because it's the most widely known REST implementation. So if I incorporate a notion of time and I say I attach something like a counter to my resource, which is the E-tag mechanism in HTTP, and I can I can use the if-match header, which is a standard mechanism to do the same, like a compare and swap operation, right? So now the response of the server can either be that it accepted my update, and then I get back the current E-tag of that resource, which can just be a number, a running number. So now I have state 2, or if something else or somebody else changed it in the meantime, I can get back this status code that probably nobody ever seen before. I for sure didn't, so when I researched this, I came across this. First, I wanted to model this manually, so that's already built in. The server will tell me that my precondition failed, and it can return me the current state of it, and then I can apply my then I can apply my modification to the state again and retry my operation. So that can make a RESTful system a value-based system. And I can even turn these into identities again, or rather, I can enable my RESTful API to refer to previous states, because they are just numbered, and I can keep a list of states I've seen. And if the server supports it, I can refer to the resource at state 1, and again, a value doesn't change, so I can just say it never expires. There's no way in HTTP to say something never expires, but I can give the largest Unix timestamp at least. So this place will never change because it refers to a value, right? And that's a really powerful thing to have. I don't know of any existing HTTP API that actually does that, but it might be worth a try. Another really interesting system that is built on the same ideas is Nix and Nixos, or RNix and Nixos. So Nix is a rather experimental but also practically useful by now package manager, and it is purely functional. So what does it mean, right? We'll see in a second. And Nixos is a Linux distribution that is built around this package manager, and I recommend you to check that out because it gives you some advantages. We'll see. So the identities in Nixos are Nix are packages, of course, and in Nixos it's the whole system. Thanks. So the whole system is an identity, and I can transition it from state A to state B. You probably already know what that means. The values are the actual package versions. So if I have version A or version 1 of some package, and then I have an update to version 2, then these are two different values, and they can be identified by means of their checksum, for example, as we all do. All distributions do that, basically. And additionally, Nix also takes into consideration all its dependencies. So it does a checksum across the contents of the package and its dependencies. And then it has a value that it knows will never change, because at that point in time, the package looked like that. And the whole system setup is also represented as a value. And change is, of course, then upgrading the system, upgrading a package. Downsides, again, space requirements, and you need to explicitly garbage collect your system. So sometimes you have to run that so your old versions don't fill up your disk, but that's okay. And the upsides are, again, far more really worth it. So I get atomic upgrades because a package that is installed is never changed in place. It's never overwritten. If it has changed its contents, then a new place will be created where only this specific version lives. And only when all these packages required to update my system are done, or prepared, only then my system reference will be updated. And then it will point to this new state. And if it doesn't complete for network failures or whatever, or machine failure, then my system is just not updated, and I can still refer to the old state. So that's basically the dream of atomic upgrades built in. I can also switch back to old states, so it creates a grub entry for every system upgrade I have, and it just jumps back to the previous configuration, because it can. There's no big deal. And I can have, of course, multiple package versions in parallel. I will wrap up quickly now and skip the Git example. It works basically the same. You have branches for identities, you have commits and tags and trees for values, and then committing and merging are the changes, so just rush through that. You have also transients here. And I think you all know, you never, or nobody of you who writes code doesn't use a version control system, I guess, because of the same problems. When you update files in place, you just lose the old version, and that's what you want to, that's what you don't want. So please also do this for your systems. Right? So only use plop when you to implement these abstractions, and maybe in resource-constrained scenarios like in embedded hardware or where you don't have much memory right now. But if you have, then don't use it. Avoid state and use these managed references I presented when possible. So if you don't have state at all, even if you have managed references at your disposal, it's even better to not have any state. Just have everything as a pure function. That's even better. Easier to reason about. So the final conclusion is, let's try to make this value-based programming approach the default and not start out with a place-oriented approach when building new systems. So this is my appeal to all of you. There are some recommended talks that explain the same ideas in a different way and more focus on how it's implemented in Clojure. I recommend watching these. They make sense from even if you're not interested in Clojure. And right, so we have one more minute for questions, and thanks for your time and attention. Sorry, I had to rush that so much. Okay, are there any questions? I think we have 2 minutes, right? Any questions? You can reach me here, of course. Yeah.
Yeah, not about the actual programming, but about NixOS.
Yes.
What is the state of the OS? To what other Linux distribution is this comparable? For example, how many packages does it support?
Okay. So the question is basically the real world use or is it possible to use NixOS in the real world? Are there many packages and stuff like that? Are they up to date? And yes, it's quite up to certain. So one of the continuous integration tests is to build Quake 3 and run an automated match to see if everything works. And it is at that level, and it's quite actively maintained. But there's no, for example, no security process in place yet and stuff like that. So it's still a bit experimental. But I definitely recommend you to try it out, maybe just in a virtual machine, so you see how it works. Another one? I know. You mean because the old version is, in NixOS, the old version is still present and can be used, but there's a security fix in a newer version, then it compromises security. That's true, of course. So to fix that, all the packages pulling in that dependency have to be upgraded as well, so that they refer to the fixed version, of course. This is, again, it produces more state or more data, but it gives you all these advantages, so that's worth the trade-off, I think.
Which is a timestamp for each node that the value passed by. So it gets multiple timestamps, each node keeps an incremental stamp for that.
Yes. The video operator was comparing this to distributed databases like DynamoDB, which use vector clocks. Well, vector clocks are to represent changes. Vector clocks are actually a coordination mechanism across distributed systems, that's right. But it has some similarities in that regard. But we can also use that in the small, so just use it in your small instead of the loop I presented originally. Use what I presented in at the end. Gives you lots of advantages and easier to debug programs. Okay, thank you very much.